Your internet speed test says you're getting exactly what you pay for, but your streams still buffer and your games still lag. That's by design. Today, I'm breaking down every hidden bottleneck secretly crippling your setup, starting with the one your ISP prays you never test. ISP throttling and data caps. You run a speed test, see your full speed, and assume everything's fine. Turns out, no. Many US residential plans have a soft data cap around 1 TB per month. Blow past it, and your traffic gets throttled to 1 to 10 Mbps regardless of your plan. You could be paying for gigabit and getting dial-up performance, which is, not ideal. That cap evaporates fast. Streaming 4K chews through 7 to 25 Mbps continuously, meaning you can burn your monthly allowance in just 100 hours of viewing. But here's where it gets complicated. Deep packet inspection lets ISPs selectively throttle specific traffic while leaving speed test sites completely unthrottled. They literally exempt the sites you use to diagnose the problem, so your speed test looks perfect while your actual experience is crippled. And those unlimited mobile plans, they throttle video right out of the gate, and after 22 to 50 GB, every byte drops to a few hundred kilobits. You blame your router, but your ISP is the culprit. At least it's just policy throttling, unlike a hardware bottleneck living inside your own house. Router buffer bloat. You can have a connection that benchmarks beautifully and still become completely unusable for gaming, or calls the moment someone uploads a file, and I can prove it. On a typical 100 Mbps down, 10 Mbps up connection, a single large upload can cause ping times to jump from 2040 meters to 200 1000 meters or more. Your bandwidth tests will still show near maximum throughput. Everything looks fine on paper, but your Discord call is stuttering, your game is rubber banding, and your web pages are taking seconds to load. The problem is buffer bloat. Here's where it gets weird. Your router is trying to be helpful by holding on to every single packet in massive queues instead of intelligently dropping them. These buffers can hold hundreds of packets, enough to add hundreds of milliseconds of delay before anything even leaves your house. So when someone starts a cloud backup, every packet from every device gets stuck waiting in line behind that upload traffic. The queue fills, latency explodes, and suddenly your gigabit fiber feels like dial-up. Modern queue management algorithms like Codel and FQ-Codel fix this by actively dropping packets when queuing delay exceeds 5 to 10 millisecond targets. Enabling smart queue management or SQM features on your router often trades a small percentage of peak throughput, maybe 5 to 15% for dramatically lower latency. You might cap your 100 Mbps line at 90 Mbps, but you'll actually be able to use it without lag spikes every time someone breathes on the network. But if you think router queues are bad, wait until you hear about the invisible delay hiding in your DNS lookups. DNS lookup latency. You have a gigabit fiber connection. Pages should load instantly, yet every time you click a link, there's this half-second pause where nothing happens. The browser just sits there thinking, you're not downloading anything yet, you're waiting for your computer to figure out where the server even is, and that's DNS. Before your browser can fetch a single pixel, it has to resolve the domain name into an IP address by asking a DNS server. On a well-configured connection, that lookup completes in around 10 to 50 milliseconds, barely noticeable. But if you're using your ISP's default DNS, or you picked a resolver that's geographically distant, or your router is misconfigured, that number balloons to 100, 200, sometimes 300 milliseconds or more per lookup. Now here's the kicker. Modern web pages don't load from one domain. They pull resources from 50 to 150 unique host names, ad networks, analytics platforms, CDNs, embedded videos, tracking scripts. Every single one requires its own DNS lookup if your cache is cold. So what feels like the page is slow to load is often your browser spending more time asking who is ads.example.com than actually downloading the ad itself. DNS over HTTPS and DNS over TLS encrypt your queries for privacy, which is great, except they also add protocol overhead. That tacks on another few tens of milliseconds per lookup. The result is a paradox. Fiber speed internet that feels slow to start because the invisible thinking time before anything loads eats up more clock than the actual download. At least DNS eventually caches, unlike Bluetooth audio, which is a permanent disaster. Bluetooth audio latency and codecs. You spend $200 on premium wireless headphones and load up a rhythm game. First note, you're already dead because the audio is a quarter of a second behind the screen. Congratulations, you just bought a very expensive lag machine. Here's the thing. Most Bluetooth audio isn't optimized for latency. It's optimized for battery life. The baseline SBC codec incurs a 150 to 250 milliseconds of delay under real conditions. In a rhythm game, that's the difference between hitting the note and failing entirely, and it gets worse. AAC, the default on Apple and many Android phones, sits around 150 to 200 milliseconds, with some OS pipelines pushing even higher. LDAC markets high-res audio, but it's not meaningfully faster and often adds more latency at higher bit rates. aptX low latency exists and theoretically drops air interface delay to 30 to 40 milliseconds, but total system latency still lands near 40 to 80 once you account for encoding and processing. And here's the kicker. Most operating systems don't let you choose your codec. They default to the slower, more robust option even when both ends support something faster. Bluetooth version numbers don't tell you anything about latency either. Bluetooth 5 isn't magically fast. The codec matters far more than the spec number printed on the box. At least you can see your cable's bandwidth limit on the label, unlike Bluetooth headphones where you won't know how bad the delay is until you've already bought them. Display cable bandwidth limits. You can drop $2,000 on a GPU and another $1,000 on a premium monitor, then get completely wrecked by a $12 piece of wire. The cable connecting your graphics card to your display has a hard physical speed limit, and when you exceed it, your system doesn't throw an error. It just silently downgrades your image quality until the math works out. You literally pay for performance that never arrives. HDMI 1.4 maxes out at 10.2 Gbps. That handles 4K at 30 Hz, but try pushing 60 Hz and it simply cannot do it without compression. HDMI 2.0 bumps that to 18 Gbps, finally handling 4K at 60 Hz with full 8-bit color, but here's the kicker. The moment you want higher refresh rates or 10-bit HDR, the cable gives up and forces chroma subsampling. Your system silently drops to 4.2.2 or 4.2.0, which tanks color detail. HDR looks washed out and people assume their monitor is garbage. Turns out no, it's just the cable. HDMI 2.1 jumps to 48 Gbps, capable of 4K at 120 Hz or 8K at 60 Hz. But it demands matching ports and ultra-high speed certified cables. Millions of users unknowingly use older cables that physically cannot sustain these signaling rates. The system just negotiates down and you never know, which is, not ideal. But if you thought your display cable was the only invisible choke point inside your PC, wait until you see what's happening to your PCIe lanes, PCIe lane bifurcation. Your motherboard has a wiring diagram you never see, and it's probably strangling your hardware right now. Most mainstream desktop CPUs give you exactly 16 PCIe lanes for your graphics card, plus 4 lanes for one NVMe drive. Everything else connects through the chipset, which talks to the CPU through an uplink that's only about 4 lanes wide. That's the shared highway every other device has to use. PCIe 3.0 delivers roughly 1 GB per second per lane. Your X16 GPU slot can theoretically hit 16 GB per second, but here's where it gets weird. On some motherboards, the moment you install a second M2 NVMe drive, the primary GPU slot gets electrically downgraded to X8. Your graphics card just lost half its bandwidth, and the system never told you. Most GPUs don't care about X8 versus X16 for gaming, but certain workloads, PCIe-based GPU compute, multi-GPU setups, they absolutely notice. It gets worse with multi-NVMe adapters. You plug in a card that physically holds 4 NVMe drives into a single X16 slot. Without explicit bifurcation support, the system might only recognize one drive, or all 4 get forced to share a single X4 link, bottlenecking your RAID array to the throughput of one drive instead of 4. Some enthusiast boards let you manually split that X16 slot into X8, X8, or X8, X4, X4, but enabling those modes often disables other devices. Your SATA ports vanish. A secondary PCIe slot goes dead. The most frustrating part is that there's no warning. No pop-up saying your GPU just dropped to X8. The system looks loaded with high-speed components, but half of them are stuck behind invisible traffic jams you can only find by reading chipset block diagrams. At least your GPU still works, unlike your RAM when it's stuck in single-channel mode. RAM single-channel limitation. Your machine can have 16 gigabytes of RAM and still perform like it only has half that much, because it does. At least in terms of bandwidth. Most desktop and laptop motherboards support dual-channel memory, which means 2 RAM sticks can be accessed in parallel to double the effective bandwidth. But many pre-built systems ship with a single stick to save a few dollars. You're left with a machine that looks fine on paper but is quietly running at half speed. A dual-channel DDR4 configuration with 2 8GB sticks at 3200 MTS offers theoretical bandwidth around 50 GB. A single 16GB stick delivers roughly half that. Same total capacity, half the throughput. And before you shrug that off, integrated GPUs share system memory instead of dedicated VRAM. That means every frame your iGPU renders is pulling from the same pool as your operating system. When you're stuck in single-channel mode, you're starving the GPU of bandwidth. Switching to dual-channel can yield frame rate improvements of 20, 50% or more in some games, for free, just by adding a second stick. Even on systems with discrete GPUs, benchmarks show dual-channel outperforming single-channel by 10 to 30%. In CPU-bound games and content creation. Here's where it gets frustrating. Your operating system will report 16 GB installed without mentioning you're running in single-channel mode. Windows doesn't care. The only way you'd know is by opening a diagnostics tool or physically checking how many sticks are installed. Many pre-builts are sold with a single module to reduce cost. It's an invisible cost-cutting measure that tanks performance in ways most buyers will never notice, bar AIM. But at least your RAM isn't actively shutting itself down to avoid melting, unlike what happens when heat becomes the problem, thermal throttling. Your CPU can hit 5 GHz for about 3 seconds, then it gets hot, realizes it made a terrible mistake, and drops back down to 3 GHz where it stays for the rest of your gaming session. And nobody told you this would happen because the box just says up to 5.5 GHz turbo, which is technically true in the same way a car is technically capable of 120 mph if you drive it off a cliff. Here's the thing. Modern CPUs advertise turbo speeds of 4.5, 5.5 GHz or higher, but the moment you run a sustained workload, temperatures climb toward 90 or 100 degrees, and the chip throttles itself back down. If your cooling can't handle the heat, the CPU settles near or even below the base clock. You paid for the turbo. You're getting the base, laptops are worse. CPUs and GPUs share the same cooling system, so when you game, both components fight for thermal headroom. After a few minutes, clocks drop by hundreds of megahertz. A laptop GPU rated for 2 GHz might spend most of a session at 1.4, 1.7 GHz. Because the CPU next to it is also cooking. Frame rates start strong, then gradually decline, the fans scream. The chassis gets too hot to touch. Thin and light laptops ship with aggressive power limits to keep noise low. A CPU rated for 28W gets constrained to 15 and 20W under load. Performance tanks. The chip is physically capable of more, but the firmware won't let it run there because someone decided thinness mattered more than sustained speed. And here's the kicker. Ambient temperature makes it worse. A system running fine in a 20 degree C room can throttle hard in a 30 degree C environment. Summer arrives, your frame rates drop, and you think your hardware is dying. Nope, it's just hot. At least thermal throttling is predictable, unlike the storage disaster we're about to cover. Shingled magnetic recording. 2 hard drives sit on your desk. Same brand, same capacity, nearly identical model numbers, one costs $20 less. You buy it, plug it into your NAS, and 6 months later, you're losing your mind because RAID rebuilds are taking literal days. Congratulations, you bought an SMR drive and nobody told you. Shingled magnetic recording overlaps write tracks like roof shingles, cramming more data onto each platter. On paper, it's brilliant. up to 25% more capacity without adding physical disks. The problem is what happens when you try to write data. Under light sequential workloads, SMR drives behave normally. Big media downloads, backups, you'll see 150 to 200 megabytes per second, but hit them with sustained random writes and the entire scheme falls apart. Because tracks overlap, rewriting one track can disturb its neighbors, forcing the drive to rewrite entire regions. One user write triggers dozens of internal writes. During heavy workloads, some SMR drives drop to single-digit megabytes per second, or less. Here's the kicker. Manufacturers hid this. Early SMR drives were labeled device managed, meaning the operating system had zero idea this was happening. You'd see a normal block device, but inside, the drive was performing absurd amounts of data shuffling. Users unknowingly deployed these in RAID arrays and NAS boxes where sustained random writes are constant. RAID rebuilds that should take hours stretched into days, small file NAS workloads became unusable, and the model numbers gave almost nothing away. The storage community now maintains spreadsheets cataloging which drives are SMR versus CMR because you can't trust the product pages. Two drives, same box specs, radically different real-world behavior. At least write endurance on an SSD is predictable once you know what NAND type you bought, which is more than you can say for the SSD wear problem waiting to punish your next scratch disk. Write endurance. An SSD can look absolutely blistering in a benchmark while being secretly fragile under heavy write loads, and I can prove it. Consumer TLC NAND supports around 1,000 to 3,000 program erase cycles per cell. Older MLC could handle 3,000 to 10,000, QLC a few hundred to maybe low thousand. The silicon itself is literally wearing out every time you write. A typical 1 TB consumer SSD is rated for roughly 300 to 600 terabytes written. At 100 GB of daily writes, a 600 TBW drive takes over 16 years to hit its rated endurance. A cheap 150 TBW drive hits it in about 4 years, which, is less ideal. But here's where it gets complicated. Many consumer drives use a portion of their TLC or QLC NAND as pseudo SLC cache. Incoming data writes fast to this cache, then gets folded into slower multi-bit storage later. When that cache exhausts, write speeds plummet from thousands of MBs down to tens or low hundreds. Fill the drive past 80 or 90% capacity, and free blocks become scarce, forcing aggressive garbage collection that amplifies writes and tanks performance further. Users running continuous video capture or scratch disk rendering on low-end QLC drives get hit with this speed reliability paradox hard. But if you think your SSD is silently struggling, wait until you see what your operating system is doing behind your back. Background, telemetry, and bloatware. Your brand new gaming PC boots up for the first time, and it's already slow. You haven't installed a single game yet, but somehow it's taking 45 seconds to reach the desktop, and the disk usage is pinned at 100%. Welcome to the wonderful world of pre-installed garbage. Here's the thing. Manufacturers love stuffing your system with software you never asked for. Trial antivirus that nags you every 6 hours, cloud backup services harvesting your files, vendor control panels that do absolutely nothing except add 3 startup tasks and occupy 200 megabytes of RAM. Every single one thinks it's the most important thing on your computer, so they all fight to load first, turning what should be a 10-second boot into a full minute of disk thrashing. But wait, it gets better. Background updaters for browsers, game platforms, creative suites, and messaging apps all run on timers, checking for updates constantly. On a hard drive, when 4 or 5 decide to phone home at the same time, your disk usage spikes, everything freezes, and you're left wondering if your storage is dying. It's not dying. It's just being held hostage by updaters that think their 5 megabyte patch is more important than the game you're trying to launch. On systems with 4 to 8 gigabytes of RAM, background processes can easily occupy 1 to 2 gigabytes before you open a single program, launch a game, or open a few browser tabs and the system starts paging to disk. If that disk is a hard drive, congratulations, you've entered performance hell. The truly wild part is that a modern machine with decent specs can feel slower than a 5-year-old laptop that's been properly cleaned up simply because it's carrying the weight of dozens of useless background processes, removing this bloatware is often the single most impactful performance improvement you can make, more effective than upgrading certain hardware. But if you think a cluttered startup is bad, wait until you see what happens when you leave 30 browser tabs open for a week. Yesad, sorry, browser tab memory leakage. Your browser is probably eating your computer alive right now. Open 30 tabs and each one is a separate process consuming tens to hundreds of megabytes of RAM. Do the math. 30 tabs at $80 million each, that is 2.4 GB. 50 tabs, you are pushing 4 GB. And that is before memory leaks kick in. Here is where it gets worse. Chrome uses a multi-process architecture. Every tab, every extension spawns its own process. Great for stability, terrible for RAM. You are not running one browser. You are running dozens of tiny browsers, all hogging memory independently. Now add leaks, JavaScript apps that never clean up event listeners, single-page apps holding on to unused objects. These are common bugs that accumulate over hours of browsing. Your browser keeps growing megabyte by megabyte until it consumes everything. When your system runs out of RAM, the OS starts paging to disk. Switching tabs takes seconds. The system thrashes, grinding to a halt. And you blame your slow computer, not the 6 GB of RAM Chrome is sitting on because you haven't closed a tab in 3 weeks. Extensions make it worse. They inject scripts into every page and maintain background processes. Install 5 extensions and you just added hundreds of megabytes of permanent overhead. The absurd part, this makes perfectly healthy machines feel broken. People buy new computers to solve what is fundamentally a software problem that vanishes the moment you close your tabs. Your browser has colonized your system and convinced you the machine is dying. It is not. It is just being slowly strangled by a single application. If you enjoyed this video and want to see more, click the video on the screen now.